Hello friend, this is Kunal. Welcome back to my channel. Today we're going to learn the most interesting topic of mechanical as well as the civil engineering, that is the shear force diagram and bending moment diagram. Before start, I would like to thank all my viewers, and if you're not still subscribe my channel, then go and subscribe and don't forget to hit the bell icon to get notification of my new video. SFD and BMD, we must have to take care of some points or the rules. So let's see. This is our rule book. Here we wrote some formulas which is used for the drawing the SFD and BMD. So let's say it one by one. First one is shear force and bending moment diagram starts with 0 and ends with 0. So let's see how it happened. This is the shear force diagram and this is the bending moment diagram. As you see, this shear force diagram starts with 0 and end with 0. Similarly, the bending moment diagram starts with 0 and end with 0. Let's see another point, that is the second A. Concentrated force or the point load causes the sudden change in the shear force diagram, and change is in the same direction and of same magnitude as that of the load, but there is no such sudden change in the magnitude in the BMD. Okay, we see it by this is the point load. It will deflect or it will sudden change, it will cause the sudden change in the shear force diagram, and the change is in the same direction as that of the load, so it is in downward direction, you can see, and the shear force diagram will deflect in same direction. You can see the deflection of the shear force diagram is of same magnitude as of the load, that is 9 kilonewton, and it will deflect exactly same at 9 kilonewton. And similarly, you can see the bending, there is no effect of point load on the bending moment diagram. So let's see the another point. Second B, concentrated moment causes the sudden change in the BMD, but there is no such changes in the SFD. This is the moment, concentrated moment, it is of clockwise direction. It gives the sudden change in the BMD, no change in the SFD. You can see here, no change in the SFD, but there is a sudden change, it is of -10 and then suddenly change to the 20. Okay, that's another other, and now the problem or the question occurs in our mind, that is where it moved, downward direction or the upward direction. So for that, if the moment is in clockwise direction, then the bending moment moves upward, or if the moment is in anti-clockwise direction, then the bending moment moves downward. If we take the x axis here at a distance x, in both cases clockwise direction and anti-clockwise direction, then moment at that point is ay into x, that is ay into x plus, that is the clockwise movement, so it is taken as plus, and similarly when it is anti-clockwise, so it is taken as a minus. Then the third point, Vf minus Vi, what is it? Shear force, final shear force and the initial shear force is gives the area of loading diagram, that is Qx. If we take the example, that is the UDL, that is uniformly distributed load of 5 kilonewton per mm, and it is the span of it is what, 6 mm. So the area under the loading diagram, that is 5 into 6, that is 30 is the our no, answer of that area of loading diagram, and the initial value of this is something like 12. So just we'll take in here, and what is 30 minus, so it is 12, so it is plus 12, and addition of this is will be the final shear force. Similarly, the final bending moment minus the initial bending moment will give the area of shear force diagram. The area of shear force diagram, if we take this, if we calculate the area of this, 9 into 2, that is 18, will be the max bending moment at another point, that is final bending moment. Initially it is 0 initial. If we put the in a final value of if I have to calculate the final value, that is mf minus initial, the bending moment is 0, so put, and area of shear force diagram, so it is minus 9 into, that is the span, 2 meter. Okay, so 2 that is equal to minus 18, it is 0, so mf equal to minus 18, and we draw it like this. Okay, now the direction, if the value of qx, that is the area under loading diagram, that is it is upward. If it is upward direction, then it is plus. It is in downward direction, that is minus. Okay, here it is downward direction, so taken as a minus. Then in bending moment it is same as area of above the axis. If area is above the axis, it taken as a positive, and below the axis is taken as a negative. And another point, I'll draw the simple diagrams will show distinguish the how we can draw the in the SFD and BMD. If the point load acting on the simply supported beam, there is no qx, that is area under the loading diagram, no area under the loading diagram, but there is some value of vx, so taken at a c1, and there must be the straight line. As you see, I'll show you. This is a point load, there must be a value of value, that is c1, we taken at a c1 in the vx, that is a vx, and it is mx, and it is of straight line in the bending moment diagram. Now if the UDL is on the simply supported beam, that is qx have the some value, that is c2, and vx have straight line, and then mx have the quadratic. Here it have the UDL, that is uniformly distributed load over the simply supported span or the any other span. So it will in Vx it will be the straight line, in Mx it will in the quadratic, that is the curvature. Now the third case is varying loading. So here the Qx is straight line, you can see this is the qx, then it is straight line, then the vx is a quadratic, that is in curve, and the cube, that is another thing. Okay, if you see the fifth point, then curvature in the SFD and BMD, there is no such curvature in SFD, we take it as a straight line, so skip it. And there's a downward then we take there is a some standard formula, d square y dx square is less than 0, then it is maxima. D square by dx square is greater than 0, that is the minima. Maxima means this direction, and the minima means this direction. It is the curvature. This curvature, it is maxima, or if it is drawn like this, so it is minima. So for that, we just have to double differentiate the mx bending moment diagram, then we get the maximum or minima. If the double differentiation of bending moment is less than 0, then it is maxima, and the double differentiation of bending moment is greater than 0, then it is minima. So for better understanding, we take an example as it is given below. Here the beam having the 9 kN load and 3 kN at its end A and E, and at B and D there is a simply supported beam at B and D, you can see, and the uniformly distributed load of 5 kN acting on the span, that is the 6 meter span on which the UDL, that is uniformly distributed load acting, and its magnitude is 5 kN per meter. And there is also one couple acting, which is 30 kN per 30 kN meter at C. So here we have to simply first step that you have to take care, that summation of moment at any point you have to just b, I just take it b, is equal to 0, then 9, it is 9 into 2, 9 into 2, it is goes anti-clockwise direction, we taken as a minus 2, plus that is 5 kilonewton. 5 when we have to convert the UDL into the point load, so we just have to multiply the intensity of the UDL, that is 5, into the span over which the UDL act, that is 6 meter, it will convert into the point load, and for taking the moment also we have to into it by the distance, that is the, and it act on the just middle of the span. So 6 meter, 6 by 2, middle of the span. Then again minus rd, this is direction at d, into, it is 6 plus 3 into 8, 0 is equal to minus 9 into 2 plus 5 into 6 into 6 by 2 minus rd into 6 plus 3 into 8. And wait, oh my god, there's something mistake here. Plus sorry, minus, oh, one more thing we forget here, that is the moment. It is of clockwise direction, so plus 30, plus 30. Then we have rd equal to 21. Similarly, we can find by summation of fy equal to 9 9 plus 5 into 6 plus 3. Then these two reactions, that is plus sorry, it is minus rb plus rd. We find out rd as a 21, so minus 21. Okay, this moment it is not a force, so we doesn't take it, and we find it 0 is equal to 9 plus 5 into 6 minus rb minus 21, so it will give you another we forget to write 3, it is also 21, so means rb is also 21. Already written wrote it. After calculating the reactions at the supports, as you see here 21 and 21, we are going to calculate the shear force diagram and bending moment diagram. First of all, the shear force diagram. So as you see, there is a point load of 9 kilonewton on the spring. So as per the second a rule of rule book, it will deflect the shear force diagram by the same intensity, that is 9 kilonewton, and in the same direction, that is downward direction. So go with this like that. Okay, then again there is no load on the dash on this span of 2 meter, so straight line will be there. Again 21 kilonewton of load goes upward, that is also point load, so same intensity with same magnitude will be go upward. uh, it is initially minus 9 and 21, so 21 minus 9 is will give the another, it is 12. Then there is a UDL up to the point A to B. uh, Before calculating the A to B, I just calculate up to the point of movement acting, couple movement acting at that point. So for that, 5 into that span, that is 4 meter, 5 into that span is 4 into 5, that is 20. It's 20, initially it is 12 and 20, 20 minus 12 is what, 8, so go with minus 8 because it is downward direction. Then again there is a again UDL over the span of 2 meter, so 5 into 2 is 10, as you see here in the initial it is 8, so it will give minus 18, so go minus 18. Then again there is a point load acting at the support, so it will move the shear force diagram up, and the intensity is same as that of the point load, it is 21, initially it is minus 18, so when we deduct minus 18 from the 21, it will give you the another answer, that is 3 kilonewton, as you see. Then there is no load on the span of 2 meter, so it is go straight. Then again there is a point load acting at the end of this, which is of 3 kilonewton, so it will again deflect the shear force diagram 3 kilonewton up to the up to 0 line, so it will be like that. Here it is the shear force diagram. Then we move towards the bending moment diagram. So bending moment, as we know, the bending moment start with 0 and end with 0. So we just have to calculate the intensity at point A. So how we calculate? It is very easy. Just calculate the area of that, and it will give you, means minus 9 into 2, that is minus 18. So go downward, minus 18. Now how we decide it is downward or upward, or it is minus or plus? Here the area is minus, so we use the minus sign here also. Then for again calculating the point at this contrafracture line, just have to calculate first contrafracture, at what moment, at what distance the contrafracture occurs. Contrafracture means the point at which the shear force or the bending moment changes its sign, that is it is plus and it is minus, so it changes its sign. So for calculating there is a two method, one is the conventional and another is the shortcut. So we go with the shortcut, but I have to tell the conventional method. For conventional method we just take axis here, and calculate the moment from left to right, or you can calculate also from right to left. You will get the point, but this will take lots of time. For saving the time we must have to use the shortcut. For shortcut there is you see there is a 12 kilonewton of load acting, and 5 load is here. Physical significance of it is what, 5 newton required. What distance will require to make the 5 newton is equal to minus 12, by which we get 12 minus 12 equal to 0. So for that we just have to calculate 12 divided by 5. It will give you answer 2.4. It is already 2 and it is 2.4, so it is 4.40. As you see, 4.40. Now it is very easy, it is 2.4. Then again triangle, the area of triangle is half base into height. Half base is what, 2.4 meter, and the height is what, 12 meter, 12 kilometer. So just calculate it, 12 into half base into height, it will give you the answer like 14 kilonewton. Initially it is 18, as you see here, in the calculation initially it is 18 and plus 14 our answer, so it will give minus 3.60 kilonewton per meter. So mark it like this. Now the time for calculating the maxima or minima, as we see in the rule book, if the double derivation of the bending moment diagram is less than 0, then it is maxima. It is greater than 0, then it is minima. So as you see there is a minus 3.60, so it is definitely less than 0 because it is minor as per the integer line, so it will give the maxima. Then we have to calculate at point where the moment act. So for that also we have to calculate the area of this triangle. So here the base is what, 4 meter minus 2.4 will give you the base of this, so it is 1.6, and the height is minus 8. So half base into height means it will give you 6.40. Initially it is 3.60 minus 3.60, and 6.40 will give you minus 10. So go with this. Now there is a couple acting on the beam. So as per the rule second B, the clockwise movement will move the bending moment diagram upward. So go with this, and intensity is same as that of the couple intensity. It is 30 kilonewton and initially it is 10, so it will move 20. As you see here, that is 10 kilonewton, initially 10 kilonewton, and 20 is the answer. Now our intensity of couple is what, 30 kilonewton, so it will give 20. Now we have to take a point at B. For calculating the B, there is a two areas, one is a rectangle and another is a triangle. So for that we just have to calculate the area of both. Calculate the area of rectangular, that is length into breadth. It is what, 2 meter into 8, so it will give you the area of rectangular. And when the area of triangular, half base into height, base is what, 2 meter, and height is 18 minus 8, it will give you height 10 meter. So half base into height is what, half into 2 into 10. So the total answer of this is what, 26 Newton, and initially it is 20. So from plus 20 minus 26 kilonewton, it will give minus 6, and it will like that. Then again for this there is a 3 into 2, that is 6, and join with this. As we see, the shear force diagram and bending moment both are start with 0 and end with 0, so our answer is right. Here it is another example, that is cantilever beam. Here we already calculate the point load at a support and the moment at the support, which point load of 12 kilonewton, and the moment it is of 30 kilonewton. You can also calculate by there is a 3 kilonewton UDL on the span of 4 meter, and at the end of the span there is a 10 kilonewton moment, you can see. So by that, taking moment at A and summation of Fi, you can calculate the all these value, that is point load and the Hg. As we calculate the point load, you can go with this shear force diagram first. We go upward in the 12. Now there is a UDL, so we must have to take incline straight line, so up to the 12. As it is 0, there is no any changes of a moment on the shear force diagram. Now it's time for the BMD. So moment, it is of it is anti-clockwise direction, so go down or up to the minus 34, as the intensity of the moment at A is 34. Now there is a UDL, there is a triangle in the shear force diagram, so just take the area of that. It is of 4 meter base, and the 12 its height, means the half base into height, it will give the 10, you can calculate it. And there is a again 10 kilonewton moment acting at the end of this, so just go above 10 because it is clockwise direction. So here it is the shear force and bending moment diagram. You can see how quickly we do it, or we did it, so you can go with this. Thanks for watching, and if you like this video, then hit the like button. It will encourages me to make the more videos. And if you have any queries about this video and my previous video, then go and write about the queries in the comment box. Again, you have any note, any kind of the notes related to the mechanical engineering, then you can go to my Facebook page, that is Mechanical Entertainment, and write there. I will definitely help you and give and provide you the necessary notes to you. Thank you once again.